In this video, we're gonna focus on simple harmonic motion. That is advanced physics. So we're focusing on the definition of simple harmonic motion, the physical system that exhibits simple harmonic motion, and their differential equation. To get all this topic, all you have to do is to hit the subscribe button, okay? Now let's define simple harmonic motion, that is SHM. Please write. Simple harmonic motion can be defined as a type of periodic motion. Simple harmonic motion can be defined as a type of periodic motion in which the restoring force acting on a particle acting on a particle is directly proportional to its displacement from an equilibrium position and always directed towards that equilibrium position. From the definition here, we're able to know that in a simple harmonic motion, we always consider the restoring force. Please take note. Whenever we are solving or whenever we are expressing the differential coefficients of a simple harmonic motion equation, we always consider the restoring force. Please take note. So let's list out the physical system that exhibits simple harmonic motion. Let's list out these physical systems that exhibits simple harmonic motion, okay? Now the first one here is mass spring system. Okay, the second one here is simple pendulum. The third one here is a torsional pendulum. The fourth one here is electrical pendulum. Electrical system, please. Okay, now we have to consider the three systems that these four systems here that obeys simple harmonic motion. Okay, these are the four systems that obeys simple harmonic motion. Okay, now let's consider the differential coefficient of them. That is differential coefficient for mass spring system. We also have to consider the differential coefficient of simple pendulum. We also have to consider the differential coefficient for torsional pendulum and the electrical pendulum. All you have to do to get the full video here is to hit this subscribe button, okay? Now when we say about mass spring system, it means that a mass is subjected to a spring. Please take note. And we have the diagram to be, now we have this to be this. We have mass subjected to this spring. Okay. Now when we have something like this class, this is a mass subjected to a spring. We call this system here mass spring system. Plus, for every mass spring system, always obey um, Hooke's law. Every mass spring system obeys Hooke's law. And what is Hooke's law here? Hooke's law said that provided the elastic limit is not exceeded, provided the elastic limit is not exceeded, that the restoring force is directly proportional to extension. Please take note, okay? So when you write this mathematically, we have the equation to be this to be F. We have this to be F, which is the restoring force, is equal to KE. Please take note. Class. But remember that writing this restoring force in SHM here, writing this restoring force as SHM equation, we say that we always refer this particular force here to be restoring force. So what make a force to be restoring force? What make a force to be restoring force is taking the negative force of that expression. So taking the negative um, of that force, the negative of this force here, that is F, will be equal to plus minus KE. Okay? Now, in this mass spring system, that is mass subjected to a spring, this is the, okay, the displacement here is not extension. There's a given displacement here. So the displacement here is downward, which is y-axis. And this y-axis is in the negative y-axis. Remember your Cartesian plane, if you have something like this point here is always your plus y. This part here is always your minus y. This is your plus s. This is your minus s. Please take note. So our displacement now, that is this extension, will change to displacement. And our displacement here, class, sorry, please, let me clean this first. So our displacement now is minus y. So I will have this to be class F will be equal to K of minus y. Please take note. So when you multiply this class, we'll have something like this. F will be equal to minus ky. So expressing this force in Newton's second law, that is this force here, in Newton's second law, expressing the force in Newton's second law, we have this to be ma is equal to plus minus ky. But we're not asked to express this force here only in Newton's second law. We are asked to express this mass spring system in a differential equation. So how do we express this particular expression here in a differential equation, please? Now we have to write this mass here is a fundamental quantity. It's not a derived quantity. This k here is a constant. This y here is a displacement, it's a fundamental quantity. Please take note. So the only derived quantity is acceleration. That means acceleration can be written in a differential equation. Now, what is acceleration? We say that acceleration A is the rate of change in velocity. Acceleration A is the rate of change in velocity. So writing acceleration in a differential order, that is acceleration will be equal to plus dv over dt, sorry. But our intention here is to write this acceleration in terms of the displacement. Please take notes. So let's know what velocity is. Our velocity here is said to be equal to dy over dt. We are taking dy here instead of the s because of the displacement we are using, okay? So replacing V, that is replacing this V here into this here, we have acceleration to be equal to class d over dt into dy over dt. So when you multiply this, I will have acceleration to be equal to class d square y over dt square. So when you do that, class, I will have this to be m of the square y over dt squared over d t squared is equal to minus ky. So making this equation to be a standard equation by taking what is at the right hand side to the left hand side, I will have this to be m of the square y over dt squared plus ky is equal to 0. Okay, so our intention now is to set the differential part to be in a standard part by dividing both sides by n. Okay, when you do that, I will have this to be class d. I'll have it to be d square y over dt squared plus k over m of y is equal to 0. Okay, but there's something you have to understand here. Whenever you have an expression like this, you can easily reduce this expression. How can we reduce this expression here? Whenever I have the square y over dt square, the focus letter here at this point is y. That is what is attached to the second derivative here. The letter attached to the second derivative at the top. So anywhere you see it apart from the differential part, anywhere you see y apart from the differential part, the coefficient of it will be omega squared. So the part we are seeing y apart from the differential part is this part here. The coefficient here is k over n. So it means that omega squared is equal to class k over n. Please take note. So when you replace this, I will have this to be class d square y over dt squared plus omega square y is equal to 0. Class, this is the differential coefficient of SHM for mass spring system. This is the differential coefficient of SHM for mass spring system. Let's solve a question here to apply this particular knowledge. Question 1, please. Let's solve this question here. Solution first. To solve this question here, we already know that there is a differential equation that looks like what we have from this particular question here. But in this particular question, that is, let's write down the question first. That is 5d square s over dt squared plus 20s is equal to 0. Okay, now let's write down this equation here in a standard way. There's an equation that looks like this, which we have derived earlier before now, and that equation is this. That is standard equation, that is the square y, but in this aspect here is s, so we have to replace that as s over dt squared plus omega square of s is equal to 0. For us to make this particular equation to look like the standard equation, that means there is something that is attached to the second derivative part, which is 5. So I have to divide both sides by 5. So divide both sides here by 5, divide here by 5, divide here by 5 to make it to look like the standard differential coefficient. I will have this to the class. This will give us the square s over the t squared plus 20 divided by 5 is 4 of s is equal to 0. So it means I have to compare this. Of course, this part here looks like this part, and this part take the place of this part here. So we have this to be s. So what's attached to s, that is coefficient of s here, is omega squared. So that means our omega squared that means our omega squared that means our omega squared is equal to 4. Remember, omega square is not angular frequency. What represents angular frequency is omega. So let's make only omega the subject. So omega will be equal to square root of 4, which is what? 2. The unit of angular frequency is rad per seconds. Please take note. You can also call this omega here angular velocity, depending on what you are relating this omega with. If you are relating omega with velocity, you call that this particular symbol here angular velocity. But if you are relating omega here with frequency, you call this omega here angular frequency. Please take note. So the first question we are asked to calculate frequency. Okay, the first question here, A, they say frequency plus there's a formula that relates frequency with angular frequency. And that formula is omega is equal to 2 pi f. So this f here represents frequency. This omega here represents angular frequency. So let's replace the given parameter here. The omega is given to us as 2 equal to 2 pi f. So class, let's make f the subject. I'll divide both sides by what's attached to f, which is 2 pi. So our f will be equal to 2 over 2 pi. This 2 here, the numerator can cancel this 2 here. So our f means that our f will be equal to plus 1 over pi in hence. The unit of frequency can also be per seconds. Please take note. Okay, now the next one here, the next question here given to us, they say we should find angular frequency. Of course, the angular frequency already calculated, that is B. Angular frequency is already calculated as 2 rad per seconds. Please take note. Now the next one given to us here, we are asked to find period. So class, since we have frequency, there's a formula that relates period with frequency. That is period t is equal to 1 over frequency, and this will be equal to class 1 over frequency is 1 over pi. When you simplify this here, I'll have this to be pi. But this is what you have to know here, that frequency is the inverse of period, and period is the inverse of frequency. Please take note. So pi as a value is the same as 3.142. The unit of period is seconds. Please take note of this, okay? So this is my answer. So all you have to do to get the next physical system that obeys simple harmonic motion is to hit the subscribe button, okay? Now let's focus on the next one here. The next one here is we listed here is a simple pendulum.